Welcome to Under the Microscope podcast. I'm your host, Pranoti Kshirsagar, and today we have with us Martin Rejhon, who is a group leader at the Institute of Physics at the Charles University in Czech Republic, based very close to Prague. Martin's research is supported by the Czech Science Foundation under the Junior Star track. He was one of the grantees in 2024. These grants are awarded to recognize and support the excellent research the scientists are conducting in Czech Republic. Very excited to speak with Martin, so please join me in welcoming Martin. Hi Martin, welcome. How are you?
Thank you for having me.
Please explain your research in super simple words to me. What exactly are you doing with graphene?
So as you said, my group is focused on graphene, which is, just to say it once again, graphene is 2D material, and my group is focused on so-called epitaxial graphene on silicon carbide, which is like a special type of graphene prepared by a thermal decomposition of silicon carbide substrate. You take a piece of silicon carbide, you heat it up at high temperatures, and at these temperatures you are able to break bonds between silicon and carbon, and while silicon atoms leaves the surface, the remaining carbon atoms creates a graphene mesh. So this is the production of the graphene, but I'm mostly focused on 3-layered graphene, because if you add more layers, then it's more fun, right? Mm-hmm. And with 3 layers, it's nice that you can stack them in different ways. So either you can stack in ABA stacking order. It means that you have 2 carbon atoms at the same position, like vertically, and the middle layer it's a little bit shifted. Or you can create ABC stacking. Each carbon atom from a different layer has different position. And what's nice is that different stacking orders raise different properties. The most interesting stacking order in my point of view, it's ABC stack graphene, because it exhibits phenomena such as ferroelectricity or tunable band gap. So it can be used for future electronics and optoelectronic devices. Nowadays, there are major ways how to prepare this type of graphene is through the exfoliation, right? So basically you peel some graphene layer and then you have to place it on the substrate, which is silicon substrate. So you peel one layer, place it, then you peel the second layer, you have to place it on top of the first layer, and then you peel the third layer, and then you apply a small angle twist to align it with bilayer below. And if you apply some twist angle, then you prepare a moire pattern. This means that then you have a variation in stacking orders. So you are getting like a triangular shapes, because energetically it's the most favorable geometry. You have one triangle which is ABA and one triangle which is ABC. And then you can do your research on that. But what's the con of this technique? It's not scalable. You are getting a small domains which are like, I don't know, hundreds of nanometers. There is no reproducibility. You have to be expert in this technique, because if you are not, then it's not easy to prepare it. But I took a scalable method, which is this thermal decomposition method. Doesn't matter the size of the substrate. So right now we are using a substrate like 5 by 5 millimeters. But if I take the whole wafer of silicon carbide and use the same procedure for the graphene growth, I will have similar graphene everywhere. And my goal is to set the right growing parameters to maximize the 3-layered area and to control the stacking order. How to control it? It's through the strain. So I would call this research more as a straintronic, not as twistronics. And we can control the strain inside graphene through the growing parameters.
You already answered my next question, which would have been which stacking order is your favorite. The ABC is your favorite when the moire pattern is what happens when you twist the 2 layers. So it's like if you want to make a sandwich or something, so you put your bottom layer of bread and then the second layer of the bread is not aligned. The corners are not aligned, right? Yes. That's what you mean with the twist angle. And then in your case, what you're doing is that you're doing 3 layers of breads on top of each other. And the bread in your case is a hexagonal shape and not a square. And then you're growing it in a way that it is slightly twisted. There is a controlled amount of twist between the first, second, and the third
Yeah,
layer.
actually,
right?
there is no twist. There is a strain between them. So you can
Okay.
imagine that you have these three pieces of bread. You shrink one piece of bread, and it creates also more patterns.
Okay. So
You don't
so
have to.
that's where
Yeah,
you wouldn't go with the
yeah.
Twistronics. You are going with
Straintronic.
the Straintronics. That is the
Yeah,
strain. And okay, because the corners of the bread, which are four in our case, represent, let's say, the carbon atoms, and the carbon atoms want to be on top of each other in a sense. So if the piece of bread, the bottom one, is bigger than the second layer, then there is strain between the second and the first layer,
yeah,
right? That is what you
yeah,
are
yeah.
going for. And then what I would like to understand is, what do you mean by the ABC? Where does that come from in our bread analogy? Let's just go with
With the
that.
bread analogy. Okay, so with ABA, you have three layers, and the middle layer is a little bit shifted to the right. Either the corners of the bottom and the top layers are aligned, but the middle piece or middle layer is a little bit shifted, right? With ABC, you have to shift also the top layer.
So it is like laterally
Yeah,
shifted. What you mean with the ABC, it is the lateral shift. But then, of course, in your case, it's not just one piece of bread. You have several pieces of bread next to each other in one
yeah.
layer.
Actually, you can align your three layers of bread, and then you apply some shear, and it will create the ABC stacking order.
Or like when you're playing cards, you have three cards and then you just spread
Yeah,
them a little, and that is the stacking that we are talking about. And that is the ABC
yes,
stacking. And the ABA stacking would basically mean that the bottom layer and the first layer and the third layer are
yes.
aligned, or in the same, let's say they are in the same plane, so to say, and the middle layer is the one that is off.
Shifted there.
It's shifted in a sense. Okay, that's why it is not Twistronics, it's Straintronics, because the strain is introduced because of this lateral
Yeah,
shift.
so lateral
Yeah.
shift, but the strain it's a little bit more complicated because the strain it's induced due to the lattice mismatch between the substrate and the first graphene layer. Also, it's more complicated because the first graphene layer it's not 100 graphene layer, but it's so-called buffer layer, which is a graphene-like layer, but it contains around 30% of sp3 bonds. Each third carbon has some bond down to the substrate. This brings the strain inside the graphene sandwich.
Okay, so like the ideal graphene, or your second and the third layer, hopefully have the sp2
Yeah.
carbons at the corners, the six corners of your graphene, but the first layer has the sp2 carbon, some of them, because of the bond with the substrate, and that is where the strain is coming from. And what you do is you leverage the strain for unlocking these amazing properties for optoelectronics or superconductivity. But then how do you visualize this? AFM or Raman or SEM? What do you do?
Yeah, so mostly we do Raman and AFM. From Raman, you can see the quality of graphene, but the lateral resolution it's poor because the laser spot is basically like 1 micron. So the best resolution I would say is around 100 nanometers or something like that. But to go down, then you have to use AFM. So we have new AFM in my lab. We have NX10 model from Park Systems. Amazing machine. Did you work with AFM during your studies?
I did. I worked with AFM during my master and my PhD work. And during my master, I think we even had the homemade, customized Frankenstein type of AFM, where you basically had to do everything all the time, like calibration, changing the tips and everything.
Yeah.
And then during my PhD work, it was a bit more sophisticated. AFM and Raman together, tip enhanced Raman spectroscopy as well. And AFM is amazing if it works.
Yeah.
But the problem is to get it to work. So how has your experience been like with the NX10 from Park Systems?
NX10 it's perfect because I think it's also good for beginners to change the AFM tip manually. You don't have to use tweezers. So that's a nice pro of this machine. You can have these pre-mounted AFM tips which are on the chip. You can take them with your hands and place it on the right spot. What's really nice that if you change the AFM tip, the laser stays at the right position, so you don't have to align it again. And you can find the same location on your sample again. So you can use short tips for some face imaging, and then you'd like to measure, I don't know, conductive AFM to see the current flowing through your graphene system. So you just change this chip and you're at the same, almost at the same position. So that's really nice.
That is really cool. So it saves you time and it's also more efficient. So you can actually spend the time changing the parameters for growing graphene or producing the graphene or fabricating the graphene. And I guess it is also important for you because you are doing fundamental research, but the aim, if I understand from you, is also to scale it, right?
Yeah.
You want it to be scalable.
Yeah, definitely. My goal is to scale it, this ABC stack graphene, because then if you come to some industry and you say, hey, I have this amazing material, what's the size of your material? 50 nanometers, so you can exist there, right? But if you come and you say, hey, I have this production line and I'm able to prepare this amazing material on a wafer scale, so then we can talk. Then the next step is to do like mass production and do some devices and future optoelectronic devices. Yeah.
So the lab to fab, taking graphene from the lab to the fabrication or rather
Yeah, that's the goal.
Yeah, that's the goal. Perfect. And the NX10 is helping you with one of the main characterization. So what else is possible? Because I haven't seen NX10, right? So other than the topography, you already mentioned like conductive.
We have also the furnace here to produce the graphene, right? So the steps are prepare graphene, characterize it, and then change the growing parameters. So what we do is we measure topography, but the AFM, it's not just a topography, right? So you can measure mechanical response or Kelvin profile microscopy, which are really nice methods. And from that, you can very fast distinguish between a number of graphene layers, because there is a huge signal variation for 2 graphene layers or 3 graphene layers. Once we have this, then we switch into a conductive AFM, and in conductive AFM we can actually see the variation between ABA and ABC domains. We can study them, and then if we compare that with Raman spectroscopy, we can say, okay, we had this strain, it creates this variation in graphene, in 3-layer graphene stacking order.
Okay, that's really cool. And I will share all the videos and the pictures that you will share with me. So for our audio listeners, please check out the video on YouTube as well, where you will see the furnace, the NX10 AFM from Park Systems, and also this beautiful maps that Martin and his team has done to understand the ABA to ABC and the different properties of it. All of that will be in the show notes. This is specifically for our audio listeners because we do have quite a bunch of audio listeners, so don't miss out on the beautiful images and videos, time-lapse videos from the lab all the way from Prague. Thank you very much, Martin. This was really great, and looking forward to having your production line grown graphene power my electronics to make them better. I think Park System also organizes NSFE, the Nano Scientific Forum. There is Asia, America, also the Europe version, right? Do you know anything about that?
Yeah, I hope so.
Well, little birdie told me that maybe 2026 NSFE might potentially probably be in Prague. Do you know anything about that? Can you confirm or deny?
I can confirm it. I think it will be a nice experience, a new experience. Prague is a beautiful city, so everybody is welcome.
When would it be? Will it be in spring or in autumn 2026 for everyone to block their calendars?
It's in September. So.
Okay. Next year, 2026, September. And what can we expect? What can you tell us already about the NSFE that you will be hosting?
That's a good question.
Amazing talks.
Amazing talks. Definitely amazing talks, amazing speakers, amazing food and beer, because the best beer is in the Czech Republic. Yeah, and definitely there will be a lab tour
Where we will see your
we'll
NX10,
see.
we will see your furnace.
Definitely. And probably I will ask also another colleagues to open their labs for the attendees. So it will be
It will be a wonderful experience. September 2026, NSFE in Prague with Marcin. Thank you very much, and I will see you in Prague in 2026.
Thank you. See you. Bye bye.